Hey everyone, welcome back to The Explainer. Today, we've got a really fun goal. We're going to take what might look like a totally dense textbook chapter on topographical maps and flip it into a practical, real-world survival guide. We are figuring out exactly how geographers manage to take our massive 3D bumpy Earth and perfectly represent it on a flat 2D sheet of paper. By the end of this, you are going to look at maps in a completely different way. So, here's our agenda for today. Section 1, Demystifying topographical maps. Section 2, Mapping India and the World. Section 3, The Language of Contours. Section 4, Drawing Map Cross-Sections. And Section 5, The Art of Map Interpretation. Let's get into it.
All right, kicking things off with Section 1, Demystifying Topographical Maps.
The core problem we're solving here is how to capture a complex three-dimensional landscape on a completely flat surface. And the answer is topographical maps. Now, the crucial point is that these aren't just, your standard road map or tourist guide. They are incredibly detailed, large-scale base maps. They're absolutely essential because geographers use them as the literal canvas to draw all other types of maps. What makes them so special is how they capture the natural world, the terrain, the vegetation, and then seamlessly layer the human, cultural world right on top of it, like our cities and roads.
Moving right along to Section 2, Mapping India and the World.
Okay, so before we read these maps, we kind of need to know the ground rules, because if everyone just drew maps their own way, it'd be absolute chaos. Let's look at India as a prime example of standardizing this process. What's really fascinating here is the major historical shift that happened in 1937 at the Delhi Survey Conference. Before that, the Survey of India mapped the whole region under the India and Adjacent Countries series. But in 37, they made a massive pivot. They stopped mapping the adjacent countries entirely to just focus on India, but critically, they started using standardized international specifications. This synced them up with the International Map Series of the world. It essentially ensured that a mapmaker in India and a mapmaker in Brazil were finally speaking the exact same visual language.
Which brings us to Section 3, the language of contours.
So, what is this visual language that makes a flat piece of paper communicate 3D elevation? It's all about contours. Imagine looking straight down from the sky at a mountain that's been mathematically sliced into perfectly even horizontal layers. The edges of those slices, those are your contour lines. They're just imaginary lines joining points of equal elevation above sea level. And the contour interval, or VI, well, that acts as your consistent elevation ladder. If the interval is 20 meters, every single line represents a 20-meter step up or down that mountain. If you're out hiking, this right here is literally your survival manual. You can glance at the spacing of these lines and instantly know what you're up against. Closely spaced contours? Yeah, you're going to be exhausted because that's a seriously steep slope. Widely spaced contours? That's an easy, gentle walk. But if you see those lines merging together, stop walking. That represents a vertical cliff or a waterfall. Also, keep in mind that contours of different elevations basically never cross each other. I mean, a single spot on the ground can't be two different heights at the exact same time, right? It gets even cooler, because these contours actually reveal the deep geological history of the land. Just by checking the shape of the innermost lines, you can play detective. A V-shaped valley, where the lines get super tight at the bottom, making a sharp V, tells us a fast-moving river or stream carved it out. But a U-shaped valley, with that wide, flat gap in the middle, that means massive, heavy glaciers scraped their way through there ages ago. Let's actually look at a real example from the source material. I want you to focus on the spacing of the lines here. Notice the wide horizontal distance between the lines near points A and B. That is your gentle slope. Now contrast that with the tightly packed lines near points C and D up on the right. That's a steep, sudden incline. This simple visual translates directly into a physical understanding of the ground under your feet. All right, Section 4, Drawing Map Cross-Sections. We've got the theoretical language down, so let's apply it. We're going to take a 2D map and slice it open to see the 3D profile. Think of a cross-section exactly like cutting a layer cake. When you look at it from a top-down view, you just see flat icing. But when you slice it down the middle and look from the side, you see all the varying layers, the bumps and the dips hidden inside. That side view profile is exactly what a cross-section is. The original textbook breaks this down into 8 highly specific steps, but honestly, we can visualize it much more easily as 4 core phases. First, draw a straight line, let's call it A to B, across your map. Second, place a strip of paper right along that line and make a mark everywhere a contour line crosses it, noting the elevation. Third, grab some graph paper and set a vertical scale to create a grid. And finally, just plot those marks onto your grid at the correct heights and smoothly connect the dots. Bam!
You've just drawn the side profile of the landscape.
And finally, Section 5, the art of map interpretation. For this last section, we move straight from theory into practice. To truly interpret a map like a geographer, rather than just staring at it, we scan it using 5 specific layers. 1. Marginal information, stuff like the scale and the grid references. 2. Relief and drainage, the hills, slopes, and rivers. 3. Land use, is it a farm, a forest, or barren rock? 4. Means of transport, roads and railways. And 5. Human settlement. By stacking these 5 lenses, we basically reverse engineer how the local people live, work, and travel based purely on the shape of the Earth.
Check out this beautiful excerpt directly from our source map. By applying our 5 layers, the human story just instantly pops out at you. Notice the red blocks indicating settlements. See how densely they hug the flat terrain right beside the massive expanse of the Ganga River? You can clearly trace the main roads running perfectly parallel to the riverbank. None of this is random. The flat topography and the water access completely dictated where this vibrant community decided to build.
On the flip side, in this totally different extract, nature is running the show. Look at the vast, green-shaded area of the Danti Reserved Forest. Notice the winding path of the Kuwardari Nala drainage stream. If you look closely at the contour lines, you'll see steep gradients in certain areas. Understanding these contours tells us exactly why major infrastructure, like the Lower Kajuri Dam up near the top, is placed in that specific spot. They are strategically harnessing the natural flow and drop of the water. So it really all comes back to this one crucial point from the text. Map interpretation is about explaining the causal relationship among features. It's not just pointing at a red dot and saying, hey, look, a village. It's about understanding why. Why is that village built on a gentle slope instead of a steep cliff? Why is the railway curving in that exact spot? It's about seeing those invisible links between human civilization and the physical geography that holds it all up. So, now that you know how to read a 2D piece of paper as a fully realized 3D world, I've got a challenge for you. Pull up a topographical map of your own city. Apply those 5 heads of interpretation. What hidden causal relationships between the bumps of the land, the flow of the rivers, and the streets you walk on every single day are just waiting to be discovered by you? Thank you so much for exploring with me today, and keep looking deeper into the world around you.